Hello students. So today we are going to perform some calculations on heat integration and optimization. So we have two examples to solve today. So we will learn all the methods that we have used to perform the heat integration. So the first question here, you have been given with two hot streams and two cold streams, and you are given with the heat capacity, the source temperature and the target temperatures. So what you are supposed to do is you need to perform heat integration and find out the pinch temperatures and also the minimum utility for hot and cold, and also we need to design a heat exchanger network for maximum energy recovery. So we are given with a delta T minimum value of 10 degrees centigrade. So the first thing what we are going to do is we are going to calculate the temperatures, the shift temperatures for both source and target temperature. As you remember from our lecture, the source and target temperature, we will use the delta T minimum divided by 2, right, which is 5 degrees Celsius in our case. So we are going to minus 5 degrees from the source temperature, while we are going to add 5 degrees to our cold stream temperatures. All right. So our 180 will become here 175, and this one will be 75, 125, 35. So we are going to add 5 degrees to the cold stream, so it becomes 65, 105, 35, 125. Alright, so we are going to calculate our heat load. So for heat load calculation, if you remember, it is MCP delta T. So heat capacity here, this one is already your M times Cp, heat capacity rate. So 180 minus 80 is 100 times 1. So we are going to calculate our heat load. So for heat load calculation, we will use the given source and target temperatures. Alright, so our next step will be we need to draw the temperature interval diagram. Okay, so before we draw the temperature interval diagram, we need to see if any repeating numbers in our temperatures. Alright, so we have repeating numbers which is 35, right? So this is the only one that is repeating, and also we have I think 125 as well here. Okay, so I'm going to put them in brackets. So I'm going to now draw the temperature interval diagram. So I arrange all the temperatures in decreasing order. So starting with 175, which is the largest number in our temperature range. It's 175, 125, 105, 75, 65 and 35. Alright, so I'm going to draw the lines. And then we need to find the delta T, summation of Cp hot minus summation of Cp cold, and also the enthalpies. So now our first temperature, stream number 1, from 175 to 75. So I'm going to draw a line because the temperature is decreasing. So this is our stream number 1. Our stream number 2, we have temperatures from 125 to 35. So 125 to 35. Our third one 65 to 105. So 65 to 105 is here. And then we have fourth one, 35 to 125. Okay, I'm going to write the CP of each stream. This is 1, 2, 4 and 1.8. So now what is the delta T? So delta T here is 175 minus 125. So in each interval we need to find the delta T. So 175 minus 25 is 50. Similarly, I'm going to calculate for all 20, 30, 10 and 30. So CP hot minus CP cold. So you need to see within this interval how many hot streams you have and how many cold streams you have. So you need to add all the CP of the hot stream minus all the CP of the cold stream. So here in this range I have only one hot stream which CP is 1 and I don't have any further hot or cold streams. So the difference is 1. In the second interval, so I have two hot streams and one cold stream. So 1 plus 2 is 3, 3 minus 1.8, so I will get 1.2. Similarly, I am going to calculate for other intervals as well. So the next step would be enthalpy calculations. So the enthalpy is delta T multiplied by our CP. So 50 times 1 is 50, 20 times 1.2, negative 84, negative 38 and 6. Okay, so now our next step is to perform the heat cascade, right? So again I'm going to write the temperatures 175, 125, 105, 75, 65, 35. So on the top we have here hot utility. Okay, so the heat will flow from top to bottom from one interval to the lower interval. So I'm going to write all the enthalpy that we just now calculated. So at the bottom we have cold utility. Alright, so we will perform the cascade now. So initially we assume our hot utility requirement is 0 and this will exchange heat with the lower interval and we keep on adding the enthalpies. 0 plus 50, we have 50, 50 plus 24, 74, 74 minus 84, negative 10. Then we have negative 48, negative 48 plus 6 is negative 42. Alright, so now which is the lowest enthalpy? The deficit that we have is negative 48, right? So now in order to make it a positive value or surplus, we are going to add this much of hot utility in our next cascade. So we are going to perform again the cascade for the second time. All right, so here we have 50, 24, negative 84, negative 38 and 6. So now we assume we require hot utility of 48. So again perform the cascade. 48 plus 50, 98, 122, 38, 0, then 6. So now this is our minimum hot utility requirement, and this is our minimum cold utility requirement, and this is our pinch point where we get 0, and our pinch temperature is 65. Alright, so now we need to identify our hot pinch and cold pinch. If you remember, in the first step we minus 5 degrees from hot and plus 5 degrees in the cold. We are going to add them back. So our hot pinch temperature will be 65 plus 5 will be 70. Similarly, our cold pinch temperature would be 65 minus 5, 60 degree centigrade. So now we are going to construct our heat exchanger network. So we can do it individually above the pinch and below the pinch, right? So above the pinch we have stream H1, H2, cold stream 3 and 4. Now we are going to use the same temperatures given to a source and target temperature, not the shifted temperatures. Need to remember this. So our initial temperature was here 180, 130, 100, 120, and our pinch temperatures are 80, pinch temperatures are 70 and 60. But if you look at this table here, our target temperature is 80. So we don't have to cool until 70. So our temperature of 80 is somewhere here. So when I perform delta T, I am going to use the target temperature, not the pinch temperature, because I am not cooling the stream until 70 degrees centigrade. I am going to cool only until 80 degrees centigrade, which is the required temperature in our process flow diagram. Okay, write down all the CP values of each stream. 1, 2, 4, 1.8. Then the delta H values. So delta H, again delta T times CP. 180 minus 80 is 100. 100 times 1 is 100. 130 minus 70 times 2, 120. 100 minus 60 times 4. And here you get 108. Now you need to remember this our CP rule. Our CP rule above the pinch says our CP of the cold stream should be greater than or equal to CP of the hot stream. Now you see which stream obeys this rule. So now CP cold should be greater than CP hot, or it should be equal to. So our cold streams are 3 and 4, hot streams are stream 1 and 2. So 4 is greater than 1, 4 is greater than 2, 1.8 is also greater than 1. So we have 3 streams that obeys the rule. So now you need to see among the 3 streams, 3 possibilities that obeys the rule, which stream when you exchange the heat will give you the maximum heat recovery. Okay. So for example, if I exchange heat between stream 1 and stream 4, maximum heat recovery will be 100. How about stream 1 and 3? Maximum again will be 100. If we exchange heat between stream 2 and 3, maximum recovery will be 120. So my first preference will be maximum heat recovery near the pinch line. So I am going to place heat exchanger by exchanging heat between these two streams. So maximum heat recovery will be 120. So this stream still has 40 kilowatt. So my first heat exchanger will be exchanging heat between these two streams with 120 kilowatt. Okay, so now second, so now again I have the possibility of exchanging heat between hot and cold. So if I exchange heat between stream 1 and 3, I can exchange only 40 kilowatt. But if I exchange heat between stream 1 and 4, maximum I can recover 100. So I'm going to choose second option as stream 1 and 4. So this stream will still have 8 kilowatt left. So stream 1, stream 4, maximum will be 100. So this will be 100 kilowatt here. So now we don't have any more hot stream to exchange the heat, and this is our cold stream with 40 kilowatt left, and this stream needs to be heated up. So what I'm going to do, I'm going to exchange heat with a utility, which will be our heater. So I need this heater with 40 kilowatt. Similarly 8 kilowatt here, heater with 8 kilowatt. So we are done with above the pinch. Similarly we have to perform below the pinch. So here our rule is Cp hot greater than equal to Cp cold. So now how many streams do we have? If you look at the table again, our stream 4 needs to be, this is the cold stream, so it needs to be heated up from 30 to 120, right? And then the stream 3 is from 60, and 60 was our pinch temperature, so we already have done this job in our above the pinch. If you can see here, 100 to 60 is already covered, so we don't have any more heating cooling that is required here. So similarly for our stream 1, so our stream 1 we already done our cooling until 80 degrees Celsius. We don't need any further cooling, so we have only participating streams, which are only 2 streams. So that is our H2 and our C4. Our pinch temperatures here are 70 and 60, and here the temperature is 40 and 30. So what are the Cp of the streams? 2 and 1.8. Then we need to find delta H. So again delta T times Cp, 60, 54. So is hot Cp hot greater than Cp cold? Yes, so we can exchange the heat. So how much maximum we can exchange the heat between these two streams is 54. So this stream is left with 6 kilowatt. So I'm going to exchange heat 54 kilowatt. So now your H2 stream still has 6 kilowatt, and hot stream need to be cooled down. So I need a cooler here with 6 kilowatt to achieve my target temperature. So this is how we are going to perform the heat integration. Okay. So coming to the question number 2. So here we have a pinch table, and we are given with the heat capacity, source temperature and the target temperature. The first 3 steps remain the same until we perform the heat exchanger network. So the part C in the question says to redesign the heat exchanger network for minimum energy, for the maximum energy recovery that feature the minimum number of units. So the first 3 steps will be the same. So here you will get your pinch point, pinch temperatures. Your pinch temperatures here will be hot pinch will be 75, cold pinch is 60, because the delta T minimum given is 15 degrees centigrade. Similarly, the QC minimum and Q hot minimum you should get around 2 to 2.5 kilowatt, 580 kilowatt. So after you perform the heat integration, you will get your heat exchanger network something like this. Here you have a heater 520, heater 60. So you can see the total heat duty 520 plus 60 is 580, which you have here from your problem table algorithm. And then you have one heat exchanger between H1 and H4, which is your 1350. Then you have another one here 1620, and then here you have your pinch line 75, 75, 60, 60. So between 1 and 3, 587.5. Then you have one cooler, one cooler 222.5. All right. So the CP of each stream from the table is your CP 13.5, 27, 53.5, and then you have 23.5. So these are your CP values, and your temperatures, hot temperature 180 to 80, so 180 to 80, it means your 80 will be somewhere here, okay, because the pinch is 75. Next is 135, then 45, then you have 60, 100, 35, 120. Okay, so these are all your temperatures of the stream. Okay, so now when we have to redesign it, what we have to look into? So what are the minimum number of units required here? So our minimum number of units required is number of streams, that are 4, minus we have 2 utilities, hot and cold, plus 2 minus 1, so it will be 5. But how many do we have? We have 1, 2 heaters, 1, 2, 3 heat exchanger and 1 cooler, so we have 6. So when we redesign, we have to remove one of the heat exchanger. So what I'm going to do here, out of all the utilities and the heat exchangers that we have, the lowest one is 60. So I'm going to eliminate this. Okay. So when I eliminate this, I have to distribute the heat to the exchanges that are connected to this heater. So I have to look for a utility path that is connected to this heater and to a cooler. So now our utility path is from this heater to this heat exchanger and to this cooler. So now when we distribute the heat, it will be affected to this heat exchanger and this cooler, right? So here will be minus 60, this will be plus 60, and this will be minus 60. Alright, so when you do that, you can recalculate and write down your values. So I'll give you some time to do that. Alright, so what will happen after that? It will look something like this. Let me erase this. So you have no more heater here. Alright, so this will become here how much? 647.5, and then here I have 162.5. Okay, so what is the rule when we perform optimization? Our pinch temperatures between the heat exchanger that connects our utility pathway, the pinch temperature has to be maintained. Okay, so the difference of 15 degrees Celsius of delta T minimum has to be maintained. So where is our new process pathway after the redesign? I'm going to remove this because now we have another heater cooler pathway. So now we have this heater. Now this heater is connected to this heat exchanger, and this heat exchanger is connected to the cooler here. Okay. So now if you look at this heat exchanger, our delta T minimum has to be maintained. The pinch temperature has to be maintained here, that it should be 15 degrees Celsius. But then what's happening here is when this cooler duty has reduced to 162.5, it is going to affect the temperatures, right? It's going to affect the temperatures of the streams. Okay. So now this heat exchanger has 647.5. So what will be the temperature here in this stream unit to calculate first? So temperature of this stream. So maybe you can just draw a simple diagram here. This is your 647.5. Okay, and the temperature here is how much you need to calculate. So here our temperature is 35. Alright, here the temperature is not known to me, and then the Cp of the stream is 23.5. So I can get the temperature value here. So this temperature here, when I calculate 647.5 equals Cp dt 23.5 T minus 35. So here when I calculate, I get T equals 62.5 degrees centigrade. So now here the temperature is 62.5, but we need 60 degrees, right, to maintain a pinch temperature. So this stream is 62.5. So and then how about this heat exchanger? Okay, so now this heat exchanger, we have temperature of 60 near the pinch, but then here the temperature is 75. But when the cooler duty is 162.5, what will happen to this temperature? Okay, so use this heat exchanger and calculate your stream temperature. So here it will increase to, so in order to maintain that delta T minimum, you have to increase the temperature. This is 62.5. So between this and this exchanger near the pinch line, if you want to maintain 15 degrees, so this temperature will increase to 77.5 degrees Celsius. If this temperature becomes 77.5 degrees Celsius, it's going to affect your heat duty that is connected to your utility pathway. So this one will be minus X. So in turn, it's going to affect your heat duty here and here. So this X you have to calculate. So how are you going to calculate? You can use any of the heater cooler or the heat exchanger. So I'm using this heat exchanger. So this is 1620 plus X. Okay, and the temperature here is 77.5. And the temperature here, this stream is 135. CP of the stream is 27. So when I solve X equals 67.5. Well, it's kilowatt. So we have to add this to our heat exchanger network. So now this heat exchanger here will have 1620 plus 67.5. Minus 67.5, and then heater and cooler duties are going to increase by 67.5. So now when we perform this kind of optimization, we have reduced one unit, and to counteract that one, we have to increase the hot and cold utility demand. So this is how we perform the optimization. Okay, so that's all for today's class. Thank you very much and have a good day.